Hey everybody, I need to make it say BAS 474. Well, I'd have to set up like multiple things, but I could make it so it said BAS 474. And I want to make it so it's hard. I don't know if you guys can see. Do you guys see like the green screen being a little bit weird down here? I don't know if YouTube fixes that. I've seen it in the video. It doesn't look as bad. But one of these days, I'll be a little further away from the green screen. It'll look better because I want to make a green wall. So can everyone see and hear me right now? It's like I can see in the video, it's got a little bit of weird kind of stuff right here. Like if you look right down there, you might be able to see like the green, but I don't know if YouTube's like fixing that, like with some sort of filters. But I can see where the green screen's not being perfect, but I want the green screen to be perfect. So I'm so glad that we have this though. I don't know, I just got some energy, just got some orange juice. So getting powered up now. I can see a tiny bit of haze. Oh no! It's because it's not perfectly lit in that spot. I should not mess with things. Do not mess with things. I may have fixed it. And now you see the top part. I think I see it up there now. Ah! Okay, let me stop. Let me stop messing with my setup, lest I make it even worse. I think about how to run this one, but I still cannot complain to you because you've been... Oh, thank you very much. I sent you an email with a couple of questions. Tyler, you did? Okay, let's look over here. Tyler's email. So, oops. Let's see. So my brain will try not to fade. Tyler, can you put him in the chat? Because the one thing I don't like doing is going to email during this, lest I like, because I don't know, like I could show like a student email being like, Brian, help, personal situation. So I'm always afraid to have email pulled up during this. Disregard your email, you figured it out. When finding the estimated AUC and standard deviation on classification problem, should we be using the output, the standard deviation? So let's see which problem you're referring to right here, and I'll give some big hints for all the problems. Let me pull up the assignment right here. So let me do that. That'd be a good start. Let's do this. Let's start. Now I appreciate you guys being so positive. We're all just working hard right now, and so you guys are doing an amazing job. Tree-based models right here. Let's go ahead and download the tree-based models. So remember, I give big hints, so we'll talk about the big hints right here. And let's go ahead and open up tree-based models. So which one are you currently working on? Which one? Tell me where you are at in the code. So number 3, bottom section. Let's take a look. Number 3. So we go right here. Let's go all the way down. Number 3. Are you doing logistic right here? So we've got right here, we need to set up our fit control. So there's the fit control already given to us. Nice and fun right there. Remember what we're doing. So do you know how long office hours are we going? Probably an hour. Probably an hour. I think I can go an hour. I think I got that in me. Problem with code not running. Yeah, Tyler, I'll go look at that after this. So probably around 8, I'll respond to your email. I'll look for your email right away, Tyler. So I'll look right there for that. We're just setting up a fit control right here. Don't worry, that's a graphical error that do try catch. It's just a graphics error, which we're not making graphics. I never understand why it appears. Wait, am I going mad? So set up the fit control, blah, 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 blah. Use train to fit the logistic model. Okay. I have the code right. I think I'm just not sure where to look to find the standard deviation. So it should be in the results. So when you run these, and I always like, do I still have my coding with Caret open right now? Oh, I've got way too much open. So I think there's the, here it is, using Caret. And this is homework tree-based models. So I always like going back to this right here. You can see we're doing, you say you're trying to look for, let me look at your question again. You're using AUC, and here's the correct one for AUC. So I always go and kind of cheat, and I grab the code because it's just much easier. So to make sure, because, and don't worry, like people have emailed me, and if you do not have a lowercase s for center and scale lowercase c and s, then you will have an error when you run your code. Since we're doing logistic right here, we can probably Google logistic in this. It's going to search the selection. We don't want to do that. So we can go to logistic. Here's vanilla logistic. Are we doing vanilla logistic or are we doing a regularized logistic? So let's go here and just kind of grab this code for the moment. Once again, never hurts to practice writing it out, but realize that if you do put a capital C for center, then it won't work. If you put a capital S for scale, it won't work. It'll crash the code. It's so easy to make those mistakes. That's why I'm always like, I like to copy paste. It's really helpful. So what kind of, we got homework, tree-based models, fit vanilla 5-fold cross-validation, fit on AUC, we got that right there, fit to the logistic, got it. So there we go. There is a logistic model, and we need to know what all the code is doing. So does everyone have, you're not the first, Connor, you're not the first. And literally, I didn't notice it till I literally was like, I had to like be so careful in my checking of it. I was like, it took me like 5-10 minutes to find it. I was like, why is this not working? And I was looking and I was like, methods correct, fit controls correct. I was running everything. And then I was like, there's a capital C, capital S. That's all it does, all it takes. Perfectly fine, just ate some food. So once again, I like to break these up. I like to make them look a lot easier to read, just so we can see what's going on with this code. Just make it look nicer like that. Clean up your code, make it look nice. So we're gonna do the same thing here. I'm gonna keep the y tilde x comma data equals, because that's kind of classic. If anyone took 320 with me, they know y tilde x comma data equals. And we have everything right here. So we now have made our code look a lot nicer, but we have to know what the y variable is. I think we're doing the electricity data set, so we're trying to do usage. So I'm pretty sure we have the electricity data set, and we need to make a train in here. So we should be able to, well, let's go do the train. And let's see if mine gives the right answer. We've seen a lot of different answers. I put in, there's the alternative sanity check. Let's see if I get the main sanity check or the alternative one. We've got the reading in of the data. We could try, Logan. I'm going to do a bunch of 474 right here. And then we could try doing that. Electricity not found. Am I not on the right? I swear I downloaded it. Did I not download that file? Where did that file go to? I downloaded it. Stat201 downloads. Oh, you know why? Wait, there it is right there. Huh. I'll be darned. What are you doing today, R? Okay, let's see here. Where's my working directory? What is my working directory today? Set working directory. I'm in documents. Why would I be in documents? Why would you do that, computer? All right, working directory is fixed. File loads. Cool. That's all it was wrong working directory. Wrong working directory, cannot find it. Uses purchases. That is correct. Ali, amazing job. So we need to go down to the purchases one, because if we're doing logistic, purchases would be a yes, no variable. And you are correct. Sorry, my brain is still booting up right here. So let's go right here. There's the tree. And so purchases, I'm trying to think of, there it is right there. And here's the data from purchases. This is something we have. Cool. Summary of purchases. Good. And then we have right here, we're going to take a look at our data set. So let's split it into 50-50. Let's use the set seed here. We just need to write our code that we're going to write train rows. We're going to use set seed. And then we are going to write, oh my gosh. We need to sample train rows and take those right there. So train rows is going to be saved from a sample of the number of rows in purchases. So we need how many rows there are in purchases, and we need 1 through that. If you run this right here, it'll just take a sample of all of those. Do try catch error, don't worry. And then we need only 50% of these. So we're going to times this by 50% to mark the train rows. And so this will be times the number of rows in purchase. So all we're doing is taking a sample of 50%. So purchase has that many observations, and then we do see that half of them are train rows now. And then when we go here to the training, we're going to take from purchase, and we're going to go inside of it and take everything but the train rows. We copy, paste, paste, and then we go to holdout. Yeah, sure. Put that in the chat. Put this up in the chat, Connor. Of course, you got it. And then I made a mistake here. This needs to be this, and this needs to be this. Okay, cool. And now we have our training and we have our holdout. We are good to go, and it's saying this should be this. Cool. We got it. We're good to go on this. So we've got our training and we've got our holdout. Kind of showed that one. I don't want to show everything, but I have to get a training and a holdout to do this. It's probably going to predict, it looks like, is the majority level. So this is the majority level for, or how often people purchased buy, because either people buy or don't buy, I believe, and purchase equals buy. Let's just take a look at the data real quick again. Oh my gosh. So there's buy and there's no. So interestingly enough, the level of interest here is no. Cool, Connor, I'll take a look at that here in a moment. And then after I grab it, delete it. I tell you what, go ahead. Oh my gosh. I'm going to put it in here, Connor, for the moment. And once I put this second one in here, go ahead and delete these right here. So go ahead and delete those out of there for the moment. So just remove those out of the chat. I should have them in here now, so we should be good. Awesome. Thank you, Connor. So just awesome. You're the best, Connor. So someone's still got to type that out if they really want to get it. So we have here, all we've done is create a training and a holdout. And as Ali so rightly pointed out, these are going to be logistic because we're predicting whether or not someone's purchasing. The level of interest is no because that comes last alphabetically. The majority level here is no. So the model is going to predict everybody no just by the naive. And we see that by looking at the holdout and the training have majority levels of no. Does that make sense with everything I'm saying to everybody? The majority level for the training is no, and the majority level for the holdout is no, because the percent in the buy, right, the percent that in the train, you're going to put the rest, oh, cool. And so we go down here to the logistic, we're predicting purchase, and we should be able to get the results right here. I'm going to take some code to in a moment. So logistic doesn't have a grid for it because logistic isn't tuning it. It's all right. It says accuracy was not used. That's perfectly fine. We're going to go in and grab one more line of code. You're really, one of your best friends right here is going to be this using caret one right here. It's amazing. If you notice right here, we can get the results of our model. It shows you how to do it. But there's a code I really, really like. It's this one right here. This code right here, which I just think is so easy to copy paste, is going to allow us to look at our best result. And truthfully, I don't need it. I don't know why I'm grabbing it. Because the logistic model should only have one result. Now, we called it model right here. I think I called it that. But there's only one best row right here. So these are the results. Ali, is this what you're getting, Ali? Are these your results for your model right here? Are these your results for your model? These probably, and I hope it's the same as mine, but Ali, how's it look for these results for you? Is this what you're seeing? And I think I have all the right code. I think I'm just not sure where to look to find the standard deviation. The ROC standard deviation will be this right here. This is the ROC standard deviation. And awesome. Great job, Ali. You're doing amazing work. And so good job, everyone working away on this. And that's what I'm here for when you're stuck, to like make sure we get the code right. And this is the ROC standard deviation. Now, what I would do is I would start making a table of these numbers. This is what I used to do when I was in graduate school, is I would go here, and if I want to compare models, I need to make a table, and I need to put into my table things like my logistic model. And so we need here model name. So let's go here. We need name of model, and we need ROC, and then we need ROC standard deviation. So name, ROC, this is horrible handwriting, and ROC standard deviation. So you would have first your logistic model, and then you would put in its ROC and its ROC standard deviation. So when you take a look at your model, it has an ROC of 0.619, it's rounded, 0.6991. And so we go back here to this, and we go and do, if it stops being mean to me. Don't troll me, computer. 1907. And then you put in the standard deviation. So the standard deviation is 0.014. So what I've done right here is I've told you my estimate of how well the model does at correctly giving the yes class a higher probability than the no class. And then I've also given you the uncertainty in it, which is I could be off by about this much. So for every model, we will get how well the model does. This is how well the model does, because this is the metric we're going to compare them on. We could compare them on accuracy. We could compare them on guess that's about it. Accuracy, ROC, which is AUC. Those are the two ones you could compare them on kappa. I don't want to compare them on kappa, but you can. So you could compare a categorical model on kappa, accuracy, or ROC. And in this class, we really focus in on ROC and which is AUC, but ROC or the accuracy. We really focus in on those. And then we need a level of uncertainty, which is this right here. So the uncertainty is just about how much we could be off. So the uncertainty just tells us, well, here is what we think we could be off by in our estimate of the ROC. So the ROC standard deviation is how far we might be off in our estimate of the ROC, because we don't know that the ROC is 0.61907. We just estimate that the ROC for like when we were to use this on new data. So our estimate of how well this will accurately order the probabilities of new data, giving the yes class a higher rank than the no class 61.907% of the time, could be off by about 1.4%. So that's how I would interpret this right here. Our estimate of how often this will properly give, this logistic model will give the yes class a higher probability than the no class is 61.907% of the time. But our estimate could be off by about 1.4% of the 1.4%, like plus or minus on our estimate. Like it could do a little better, it could do a little worse. So you want your standard deviation to be small because that's less variation in how much your estimate could be off by. Does that help a good bit, Ali, right there? Does that help make sense of what's going on with these numbers, what they mean? And then you would simply just have more models. And as you write down more models, you would see which of your models do the best. And the way we see which model does the best is we just compare their ROCs. Good job, Ali. And so I like to make the list right here. I wish we asked you guys to do this, but this is the way I would always present it. And then you could look at them and be like, okay, and I'd probably rank them based on ROC. Like, and you could do this inside of R. You could start making a data frame of it. Like, here, I'll show you. What I would do is I would start creating a data frame inside of R. And actually, you know what you could do is you could probably do this. I wonder if we make a data frame right here. Well, let me do this. Let me try this. Cool. And then what we need to do is we need to add to the end of this row. At the end of this row, we need to go, it has 1, 2, 3, 4, 5, 6, 7. So we need to go to row 1. That's right? Rows, columns, yep. Brain is slow and I have to think about that. It might get mad here. Oh, it didn't get mad, good. Because it can create that. And, oh no, that's bad. I miscounted. Always look at what you do. Always look at what you do. Cool, that did it. And variable 8, so names of DF, position 8. And then we check DF. There we go. So you'd have to update this as you go, but you could do this inside of R right here, and then you could actually sort this data frame you're creating by ROC. So I might do this as I do remaining problems, but if you take each best row of what you create and then start putting it inside of a data frame, that is probably one of the best ways to present this. So why write it down when you can just take each best row you create and then store what the model type was? So you see all I'm doing is putting the model type, and I guess for best practices, we might want to put like, maybe like that, or everyone puts, I don't like underscores. I've never liked underscores. But that'll just change the name of that right there. So it's a little easier to tell that it's not two things right there, just since it's connected. But I would start storing all these, and then once you get a bunch of different models, you can just look at them all together. So I think this is a great suggestion right here. Frankly, I don't know why we're not doing that. It's just really good for presenting stuff to start making a data frame. And then all you would do is you would go right here, and it's probably going to get mad at me if I try to store into that data frame now. You see, that's just a row. So what I should be able to do, if I had another model, I should be able to concatenate and put something like, I guess we could do like a tree. This is not a tree, but so now if I were to do this, and if I were to go to row 2 here, yep, it worked. So if you notice here, I can append on another row. I'm just pretending I did another model, and I could store that other model inside of here. as another row, but I would have to specify in the last position, like I'm appending the results of the model right here, and then I'm attaching what type of model is after this. Like here's the results of the model, and then I append it onto that vector because I'm concatenating a vector to it. I'm putting on tree, and then I'm storing it into the second row. So I'm saying write the second row of this data frame to be the results of the model with the type of the model after the end of it. So stuff like this is really good advice because you could go through here and you could do something like a forest. Like if you did a forest, does it have, I think that's how you spell it. We'll say it is. And then you could do that. You could do here boosted models. And so you can do all these different models. And as you do these models, you could just write this code right here. And at the very end, you could view the results of all your models. And once you do this, what's even cooler is you can go here and just sort them. You see, you can't sort them now because they're all the same, but you could sort by your models or click inside of here and view it visually, which I really, really like. Still, they could do a print of that or wherever you want. So Connor, which questions do you have? Which questions, Connor? I think you had a few questions, but always think about how you're presenting stuff, especially because that's really big for like, what's it called? Milton scholars and all that good stuff. Like really, like how are you presenting this? Grad schools, how does it look? How does it thing? Could you go back to number 7? Sure, let's do number 7. Was that the one? Is that the one you just sent me code for? So number 7 is, why is there an 8 there? The models were trained to maximize the AUC instead of the accuracy in this case, and for good reason. Why does maximizing the AUC versus the accuracy make sense here? And I think we're trying to see if someone will purchase, right? So are you talking about this one right here? Am I correct on this? Is this the one you want to talk about? It's a very, oh yeah. And so I'll just say this for anyone watching right now. The reason we would maximize on AUC is because we will put the people who are most likely to purchase at the top. So the people who receive the highest probabilities are the ones most likely to make purchases. So we have to correctly order things. So it'll make more sense because we're so concerned with the ordering. So when we go for the people who are going to make a purchase, we're going to pick the people with the highest probabilities probably, and our model's going to work towards that. Is there another number 7? Numbering's been weird. Where'd the 7 go? Which one is it you want me to do, Connor? Like, what's it start out with? Is it random forest? Is there a 7? Wait, here we go. Here we go. Find the error on the holdout, right? Find the error on the holdout. This is what you're talking about, right? Okay. So out of curiosity, let's find the errors on the holdout. So what code are you using for this one, Connor? What code are you using for this one? Because I helped someone out with this one via email earlier. What function did you write? Show me your function. You probably got it. I mentioned this in class today because I kind of alluded to this. And then you're always free to write code and then you can delete it. Yeah. And so this one right here, if we want to find the error on the holdout, we have to write a small function. Whoa. And then go ahead and delete it out of the chat here, Connor. Oh my. Okay, let me take a look at this. I like your I don't know. Okay. So, you're doing a super save. I should have never taught you guys super save. I think we can do this on this line. I think that'll be fine. And then you got a for loop inside of here. And then you're still inside of your function. After it for loops out, I think I found the issue. I'm seeing some logical, wait. Oh, you're writing paste. Data GLM net. Wait, okay, this looks closer. Something going on here. Oh, there's more to it? Oh my gosh. Connor, amazing work. Oh, Connor, I wish we had office hours still. I think you did a lot of good work, but I think you might, I'm reading out the code here. Let me see here. And then you've got 2 vectors. Is that before it? Okay. That goes what I was about to say because I see the creation of the vectors. So that's where I was getting confused because I was like, wait a minute, we're using something that, okay. And then we create 2 blank vectors right here. So you're creating a data frame to hold the generalized of the linear model, the RMSE. Oh no, you're seeing the RMSE holdout. Cool. And I'm reading your code right here. You're going through the length of y, so you're doing it 4 times. So all this is 1 through 4. So you're starting by storing into IDK, which is just a blank vector position, and you're storing the column name. Oh, and this should be a new line right here, right? Yeah, that's a new line. And then that'll still run right there, right? Okay, good. Spaces are losing themselves. And then I don't have all those. Okay, I think I see what you're doing. You're saying this is the name of it, and then this is. So then you're gonna store position 1, and you're gonna go through there. You declared all variables in the data frame above. I think you did this a really hard way. I'm gonna show you do it. You ready? So let's make one of these models. So we've got like the GLM, right? Or the GLM net, right? So thank you, Connor. You're awesome. Like, yeah, I appreciate it. So don't want to give away too many answers. But you've got the GLM, you've got the GLM net. So let's go back here. We've got our data frame loaded in. Here's the GLM net grid. So we can do the GLM net. Once again, I'm going to do it the easy way. I'm going to go over here to the data mining with caret. I'm going to type in GLM net. And when we go to GLM net, we're already on it apparently. And you can see here we've got the expand grid, we've got the variable, and we're just going to take this right here, and we won't worry about plotting it. We can look at the plot of it. I was mentioning this last class, and my brain just broke. But let's look at the plot of it for the heck of it. Why not? So we're going to go right here. We're going to put in the GLM net. All we really need to do right now is clean up the code. Always like it when the code looks nice. So we can make this look a little bit nicer too. And we've got here that something's being hashtagged out. Doesn't like that. You checked your answers. Awesome. And are they right? Kind of should give you 10 million points. That function right there is pretty awesome. Put it right here. Yeah. Hey, if it works, it works. That's what we always say. If it works, it works. So code works, you're good. That's all we care about is code working. And so we need to predict usage, I believe. This is usage because it's the electricity data set, which means I need to go and make a subset of it. You know what I'm going to do is I'm going to take my data right here, and you see I've already got this. So this is where once you write a code, you don't have to write it 20 times. This is what I wrote just earlier, and then I'm going to take the electricity data set and go here, and that should be good. We want to go to electricity, and we want to do a 85% split. So we have to do an 85% split. Now, if I got everything right, I think I do. And are we using seed 474? Seed 474. So we should have everything correct right here, as long as I didn't copy paste wrong. And now we look at the dimensions. We've got those dimensions, it seems. And then we look at the output, and we have the second sanity check. Do we not have either sanity check? Oh my gosh, what is going on right here? So let me see what's going on. Do I have the... Connor, I might have the third sanity check because I updated this R. My R version is the super new one, so I might be outside of it because I've got the version... On the first one, it is sample of 500. Oh, it's only a sample of 500? Did I get it wrong? So let me look at my sizes right here. Oh, let's see here. It's 5,000. So your second argument is 5,000. Oh, haha. Jeez. There we go. Went too quick. So let's go here and go that. There we go. Thank you, Connor. Correcting right there. Oh, I got the first sanity check. We're good. So many different sanity checks. Sorry right there. So you see, that's why people are like, wait, I think I have it right. And you're like, nope, it's not right. So I just read it way too quickly right here. But we're just doing a sample size of 5,000 million points again, Connor, right there. And now we have the correct thing. So once again, this is just how much we're taking right here. Usually we do like a percentage, but not today. And so now we go down to where we're making a model right here. And we're seeing that we're making the elastic net regression. Elastic net, you need to know, is what kind of regression. So let's see in the chat, Connor, what is elastic net for a million points? Elastic net is this kind of regression. Elastic net is this type of regression. It could be logistic or linear. We're using it now for linear regression. But elastic net is going to be this, regularized, which means we're controlling for the bias variance trade-off. Yep. Regularized regression, bias variance trade-off being controlled for right here. So we should know that this is bias variance trade-off. And we go right here. Error, input the following, cannot compute cases for regression. What's going on? Let me double check right here. Train data, make sure my train data is right. Should be train data. Usage is there, good. And we have alpha and lambda, GLM net, center and scale. Let's look at it again. Did it not make the model? Error and sensitivity, data predicted, data observed, level 1. Do we run everything above? Let's run everything above. Cool. I think there was some code we had to run that didn't run. Yep, there was some code that didn't run. So user error again, but we had some stuff. I think we nulled out some variables. If you take a look at it, if I'm remembering correctly as my brain boots up, if you look at right here, there's the list of the variables, and then you see we nulled them out. So it was kind of a rank deficient matrix for those watching. We just had things that could not be used. So it said like, yep. So since we nulled stuff out, I didn't run all the code. I merely ran this. And so I ran all the code and it fixed it up. It fixed it up. So kind of interesting. You see what happens if you don't null stuff out. Your model's like, nah, not dealing with it. Can't deal with that right there. Not doing it. Ain't going to work. So we go right here and we plot it. And this is kind of a cool plot. Let's open up the window. What you're going to see here is you're going to see all the alpha and lambdas. And I want to talk about this more. We've still got 3 classes. We don't have that much more material left. We're going to do neural nets. I think we're kind of pausing there. So I really wanted to get everyone up to date on all the assignments. But with this plot right here, in valid graphic state, what are you doing, computer? It's just one of those days. Plot GLM nets. So we called it GLM net. Invalid graphic state. It's something about my palettes. That's weird. Huh. If you were to create a data frame that is the same dimension as the one you created that also pulls the column names, what would you suggest? Well, here's the easy way to do it right here. Now, so I like how you're doing with a loop. I think that's a really good idea to loop through your models. But what you want to do once you have your GLM net is you want to go and you want to take your best rows code that we already have. We already have our best rows code. So we're going to go and take the best rows code from this right here. So we're just going to take the best rows code and we're going to use the model name for this. So let's go back up to the output with our GLM net. And here we are right here. Something's wrong with my graphics today. And we want to change this to GLM net. And we want to look at the best one right here. So what you want to do right here is first off, so we're just kind of completing this problem with the GLM net. And this tells us how this model does. And you notice we get a root mean square error. We see an alpha of 1, which alpha is going to be the mixing percentage between lasso and ridge. We see a lambda of 0.03, which is the regularization penalty, which I guess maybe it's not too large. It all depends. So there's the regularization penalty, and there's the mixing percentage between alpha and ridge. And then we see here the root mean square error. So the root mean square error is what we're going for. That's the big thing. So when you want to find out how this model does on new data, you have to compute the root mean square error. So what do we need? And remember, this is quantitative. I can't say that enough. So dev off, I'll run that. Will that fix the plot? Connor, 20 million points. What in the world? What is the dev thing doing? 20 million points, Connor. Amazing. I was like, I don't know how to fix that. I was like, I haven't seen that error before. Connor's Googling in the background. Connor, 20 million points. Thank you for fixing an issue I had no idea how to fix. I had never seen that issue. Hadn't showed up on this computer before, so I didn't know what was going on. And so you can kind of see where our model is that we'd want to use. It's amazing. Stack Overflow and everything's really awesome for fixing issues. So, yeah, it's just such a random, 343 votes. So the training data is not necessarily always a certain proportion of the data. Yeah, you can do a certain amount. There's so much literature on what the training data should be. If you have a very large data set, you could use a very small amount. You could use a very large amount. You know what? Oh my gosh, I should say this. This is the coolest thing ever. I wish Dr. Seaver, man, I just wish he was teaching more classes, because you know what Dr. Seaver says to do? It doesn't look like this. Oh no, that might be an issue. Dr. Seaver says we should use like 5 holdouts. So Dr. Seaver, if he had like 5,000, or do we have 50,000 observations here? Something like that. If Dr. Seaver had 50,000 observations, he would probably create holdouts of like 5,000 each. He would make his model, he'd make 5 holdouts of 5,000 each, and then he'd make his model on 25,000 observations, and then he would do holdout testing on 5 different holdouts. So he'd get 5 different RMSEs on holdouts. That's what Dr. Seaver suggests, and he's a doctor, he's a PhD in the field, but he would be like, we want to run 5 holdouts because we want really good evidence it works on new data. Like, we want to test it 5 times. So think about how tested your data is. Wouldn't that increase the variation? Well, that's the thing, is because if a holdout has an outlier, it could work dramatically worse on that holdout, because if there's like an extreme point that has a huge residual, then that'll have a big root mean square error. It'll add a lot to the root mean square error, which is highly inflated by outliers. So Dr. Seaver would suggest 5 different holdouts to get a good estimate of how it works on new data. So that's what he would teach me. We don't teach that now. It's not in Petrie's books or in Petrie's slides, but you can always make more holdouts. You can make 5 holdouts. Yeah, after it's been tested on 5 holdouts, that's the thing. And Dr. Seaver would do that in his capstone class, which I do support, but you'd be very certain. If it works on 5 holdouts, you'd be like, it worked 5 times in a row. It's going to work on new data, as long as you're collecting from the same source. Like, if you all of a sudden change who you're working with or something, then data changes, and you don't want to do that. Make sure you minimize variation. It looks like this model right here. If you notice, we're on the red line. The red line has a alpha of 1, which is the mixing between the lasso and ridge, lasso being the absolute value and ridge being the squared of the coefficients. And what are we talking about right here? We're talking about the penalty we put on it. So here you notice, especially up here, is that 0? Oof. So that did really bad when we only used the one type of regression. So we really have to do some sort of mixing, or we want to go straight to the other type. Can't ever remember if 0 is lasso or ridge is 1. If I look at the equation, I can tell you, because it's just, you can see where the ridge and the lasso is in the equation. But other than that, it's just the mixing percentage. And you'll notice right here that we do kind of get this bevy right here. So, and this might be slightly different for people. I don't know if it uses a randomization procedure, but that's got it. So how about writing this code to figure out the root mean square error on the holdout? The root mean square error on the holdout is going to be the following way. So to figure out the root mean square error on the holdout, which is very, very important here, we want to go and we want to do predictions. We want to do predictions on the holdout. Not that. My brain's breaking. We want to predict. The first thing you put in is your model. This is the name of the model you are using. So I'm giving the name of the model I'm using, and then I want to do predictions on new data equals holdout. Now, here's probably an easy way to do this right here. With new data equals holdout, that gives me the predictions, and I'm going to store this right here, and I'm going to call it y hat. So this is like a way of breaking down the steps just to show you what I'm doing right here. So I've got my y hat values. And then we go right here and we store in the y values. The y values are the actual values of y. It goes back to notation in 201, and we're just going to take the actual values of usage. So if we want to get the error, we can just do the y minus y hat. So that's the actual minus the predicted, which is a residual. So these are the residuals, which are the errors. I've now just created an error term. So now if we want to find the root mean square error, let's start with the root. Root is going to be, we're going to take the square root of everything. So let's take the square root on the outside here. So there's the square root. And if we want to take the mean, and we take the squared errors, so sums of squared error squared, or oh my gosh, error squared. So if you look at this right here, we have the root mean squared error. So this right here is my root mean squared error for the holdout. Now we should compare this to the original data to see how it did. And wow, how did it do on new data? Interestingly enough, something interesting happened on the new data. So how did it do on new data? And you know what I would probably do? I would probably do the following. I would take this. What'd I do? There we go. Oh, it turned into a list. I don't want that. Oh, maybe it's this. No. Well, let me store this. Oh. What do we have right here? There we go. There's this. There's got that. Let me call this root means squared error holdout. Okay, there's the root mean squared error holdout. Let me call this results. And let me go here to this. Let me say names, root mean square, holdout, and it's only got one, so let me call it, and then let me check it. Cool. So now we've done that, and then let's go to results, and let's append to it root mean square holdout. Why is it turning into a list? There's that. There's that. Did see the first one has a list? That's weird. So let me do this. Let me take results and turn results into a data frame. And now let's try. Now you know what we can. I know what we can do now. We can go to row bind and df, comma. Probably could have done it that way too. Let's try that in a moment. What do we have? What do we have right here? Didn't do what I wanted. Why is my brain not on? Oh, we want to do C. Column binds. So there we go. And I think it just looped the page. There we go, right there. And why does it say 185? Is that the 185th row of the data frame? I think there's a question too. So I think this is the 185th model. Wow, that creates a lot of models. So yeah, that's the 185th model it tried. I know I miss office hours too. And does this make sense what I've created right here? You can remove the row names if you want. What do you say, right? What do you do to remove row names? You can overwrite them. Like you could go here and call this df again, like overwrite your data frame, and then go to row names df, and you could do this, and then go here and go to null. Will that null them out? It's just one now. It turned it to one, but I guess it keeps row names. I'm trying to think of a way to null out row names, but it might need to know it's the 185th model. Carson, it's fun, Carson. It's good to see you in here, Carson. But you know, here's what we did, Carson. You know how we did regression, Carson? You remember back at the start of class we did regression. Right now we created how many regression models did we create? We created right now, let's look at how many regression models we created. Does anyone know in 474 to know how many regression models we created? What would we look at to know how many regression models we just created right now by doing this elastic net regression? Exactly. We created 187. Was it really the last one? No, it was the 183rd model or something like that. That was the one. So, oh, there's the decimals. It was like 180th model or something like that. But we created 187 different models. And so this right here, there we go. Was it? That's weird how the numbers turned out. Maybe just turned the, yeah. But it's data mining, and we created all of these different regression models right here. And so we can look at how these regression models do. And the RMSE is actually used in 201. It's very similar to another concept. How you make it empty. Oh, do an empty vector on it? Oh, thank you so much. What is a concept in 201 that's a lot like RMSE? What is a concept? Another 10 million points right there. It's storing one in it. It's currently just storing one. So I know. Maybe I'm just going mad. It might just do that by default, but you know what? Let's go look at DF. I am overwriting it. The concept in 201 we use that's a lot like RMSE is right next to it. They're not the same concept, but we would gauge models in 201 by R squared, and then in 474 we're gauging them by root mean squared error. And in 320 we talk a lot about sums of squared errors. So these concepts right here, you notice R squared right here. So here's what's really interesting, Carson, is if we were to look at all of our models, let's go ahead and look at all those models right here. And we've got the GLM net results. So I'm going to take these GLM net results right here, which is I created a generalized linear model elastic net regression. I'm going to call this DF, which is stores it into here so I can take a look at it. And you can look at all the R squareds for all the models. So here's all the models we created and all the R squareds of the model. I know, Carson, hey, if you like this stuff, it's so much fun. We created all of these models right here, and you can look at all their R squareds, and you can rank them easily by R squared. And you can see the one with the best R squared is this one. I think it's the highest R squared. They're all very similar. And this is mean absolute error. Then we have standard deviations right here. Every one of these metrics that we can look at, root mean square error, root R squared, and MAE all have standard deviations, which your standard deviation is just your measure of uncertainty. And then you could make a z-score from it by just comparing multiple models. So trying to do this homework, but I keep getting distracted by what Brian's doing. Just awesome, so good. I'll try to stop distracting people. Which one are you working on, Andrew? Can I help you out with it? What can I help you out with? And these are the tuning parameters right here. So the alpha and the lambda are things we use for tuning parameters to tell us like how we're going to make our model. It's literally like dials on a stove, and we're just trying different settings. Imagine if you were playing a game, Carson, and you tried different strategies to see which one is best. That's your alpha and lambda right here. Alpha and lambda are different strategies you're trying. So as you try different strategies, you see how they work, and then you can do comparisons based on some sort of metric, like to see how well it works. Object, not row names. Oh my gosh, is that it? Is this an analytics? Yep, this is BAS 474. So this is analytics right here. And then we do model comparisons to see how they work. And we try to explain things and predict things, and we make better models. And literally, this is what they're doing with all of the COVID-19 stuff. You guys, everyone probably loves when I bring that up. But if you look at all the models, I'll go, that's, I got all crazy with ads. Let me put it over here for a second, then we'll look at, they're showing Tennessee. Wow, is this new cases? We've been doing well in Tennessee. Wow, Tennessee is, thank you, Google, for the good support. Man, New York is so high on cases. Sorry, New York. Let's look at Knox County has 173 cases with 4 deaths. That's really sad. At least our death rate's very low. So where is the... Here it is. Looks like tonight we're going to pass 2 million cases worldwide. 2 million. And where's my graphs at? Graphs. We've had some good number days lately. Where? Oh, I know it is. It's the other side. Let's go look at that real quick. I'm distracted for a moment. Where? World, is this it? No. Oh, I think I found it. Because I'm actually highly interested in these graphics, like how they're turning out lately. Found it. Okay, cool. Whoa, everything changed. So, I'll always say, I have a 97 on homework, but I still haven't started the quiz. Is the code you just wrote what we're using for number 7? I believe so. Yep, the code I just wrote. Are you talking about where you have to do the comparisons of the models? Let's take a look at that again real quick. And sorry, I've been distracted. This is where, so this right here is the code you need right here. This code is what you need to find the root mean square error on the holdout. So if you look at line 149 right now, line 149 gives us the predictions. And so Carson, you remember when we did actual minus predicted? This right here is actually a what? Carson, what is that right there? The actual minus the predicted. Because I found the predicted from the model, which is the y hat, and then I found the actual right here, which is the y value. So I have my actual minus my predicted, and this gives me all the errors. We're calling it error for the moment, but it's just a what? Actual minus predicted. Think of the word that comes before it. So it's all what? Is what's going on? I thought it ended when we went on live. I saw kind of they're doing amazing. Thank you so much. And I guess Andrew, should we get Andrew involved in it too? So seriously, great job, everybody. So we have a bunch of people helping out, everything. I can start up a Zoom. That's awesome. Connor, you're awesome. Carson, so good to have you in BAS. And if you didn't figure it out, it's all right. This right here, the error right here, I know. This right here would be the residual. So the actual minus the predicted is a residual. Remember, residual wrap, residual equals actual minus predicted. So this would be the error right here. The error is the residual. So all we're doing is finding the predicted and the actual, and we have the residual. Yeah, you see it now. I knew you'd see it when I said it. So if you look here, all we're using is our model to make predictions. So like we never, this is what I was saying in 201, is I don't solve stuff by hand. I can get all the predictions from my model like this. I can get all the actual values from a model like this. Those are all the actual values of y. And then I can get all the residuals like that. There's every residual. And then I can store the root mean square error just like this as a value. And there's the root mean square error for all the values. So I can instantaneously solve all this as long as I know how to do the formulas. I don't have to solve it by hand though. Like you can ask them, we so rarely solve stuff by hand. If you're solving something by hand, you're usually just showing you know how to solve it. So we might ask people to solve something, but it's just to be like, show you know how to solve it on a very simple problem. We won't ask you to solve something complex. Like you look at how many observations this has, it has 50,000 observations. So we're never ever going to solve anything by hand that has 50,000 observations. We should just know how to write the formulas and how to solve it out, and why root mean square error, if you look at it, root mean square error is the root, here's the root of it, in the mean and the squared error. So you see the root of the mean of the squared error. Root, mean, squared error. So it is what it is. It's the root of the mean of the squared error. So if we write it out properly, we'll get it correct, and we just have to know, well, we just take the root of the mean of the squared error. And so it's kind of nested inside, like here's where we're squaring the error. So that happens first inside of here due to the parentheses. Then we take the mean of all this, which just gives us one value, and then we take the square root. So the square root of 700 basically is going to be about that right there. So it's the root of the mean of the squared error. And the numbers are looking better. How's those projections looking? So we're hitting the peak of the curve, it looks like, and we're bouncing up and down. There's that much volatility in it. Do we already have numbers on today? We're actually lower. Oh, no, it's still projected. Have they not updated this yet? Are they not? Wait, you need to update your graphics. You need to put it to the most recent date. Check these things. Check the other one. So these are all projected. This only has till April 11th. I don't know why they haven't updated their models. So I'd like for them. It's updated on the 12th. Okay, good. Well, it's the 14th now. I need the numbers. I need to know the numbers. So if we're not making 100 on the quizzes, but we still have in the 90s, will the average for this final still be? Yeah, Julian, great question. Vandy released graphics, cool. Connor, if you can put that in the chat, that'd be awesome. What are Vandy's predictions? I'll try to find it over here. Julian, you are doing great, and I might extend these because so they've got a predictive model. They've got modeling for Tennessee. Glad Tennessee's doing well on it. So I've got dates on this right here. Let me look at this. How are we looking on this? Oh, there it is right there. Let me pull this up. Cool. Yeah, here it is right here. This is the page I was on, and then this is it right here. So today's date. Oh yeah, they did release it. So this is if we lift, assumes transmission numbers increases. So the transmission number, from what I've seen, needs to be about 1.06. I mean, it'd be great if we keep it below 1, but we need to drop it. Maybe it's a different, no, I think that's a different number I'm thinking about. So average number of people infected per case, March 5th through 8th. Yeah, if you look at this, this is where Tennessee COVID-19 protection transmission. Yeah, it's additional reduction scenario assumes transmission numbers continue to fall. I'm surprised the model is that flat. That shows better? Cool. Yeah, I think so, Carson. I think a lot of whoa, what's going on right here? Got a time-lapse graphic right here. So, okay, we're looking at the y-axis right here is kind of a log scale. Yeah, it's a log scale, it looks like. Of course it is. So the y-axis is a log scale, and we're seeing new cases. So, and this is total confirmed cases log scale. So we've got a log scale on how many cases there are. So I wouldn't get too excited by the sudden dip right here, just because that's based on little data. I'm not saying we shouldn't get excited. I mean, it's good, and it's like days in so many cases. Like, I wonder when they started. So data of current, and we really started building up our cases on. So South Korea started on the February 20th. We started on March 15th or so. So South Korea is 2 months out almost. South Korea is almost 2 months out right here. So that's 2 months right here on South Korea. And we're starting on March 15th or so. So we're barely a month out. And where does South Korea hit this peak? They hit this peak. They hit that peak about, yeah, we're about on their same track. But you notice they're not fixed. They're not finished with it. So this is also right here. Same graphic. Am I going mad? Oh, it's just adding in another thing. Metro Nashville. Oh, so Nashville got hit pretty hard. Social isolation stuff. So I mean, the truth is, succeed with the training data. Yeah, there must be some randomization when the modeling is trained. Yep. Yeah, I think I made a mistake. It's a good question, Julian. I don't know. I don't know the answers to any of these questions. That's a, I don't know. There's a lot of BAS, Carson. I think we're like the third largest maybe. And this is the kind of stuff we do right here, is make models like this and make graphics. You can actually do stuff like this inside of R. You can make time-lapse graphics. So what you could do, I wonder if anyone's done, oh, cool. Someone's already done it. Is that ggplot? Whoa, what is this? Okay, I'll show you guys here in a moment. Yeah, here we go. So, and they have the code in here and everything. Cool, we'll show it. Okay. So if you notice right here, they're showing Italy, Iran, and how they have this standardized. Good, this is probably standardized by, so, blah, 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 blah. And is it only up to, oh, that's when they started. I don't know if that's the start of the data frame or not. I guess because you're out of state. Oh yeah, well, anytime. Second part of the homework, since we can only see one section of the decision tree. Yeah, let me hop back to that in a second here. This is all done via R. So if you're looking for how to do, model the data set inside of R, we see some regressions. We see some predictive modeling right here. Linear regression modeling. We see more graphics. But this right here is, oh wait. Is this year on year off box office? Yeah, cool. Oh, this is the box office? Yeah, of course the box office got destroyed by it. Okay. After 5, would you mind explaining the difference in the models that 6 is talking about? Let's hop back to the assignment. Can you explain number 5 on the second part of the homework, since we can only see one section of the decision tree? So what is going on with number 5? I think this is the one that was being mentioned today in class. Are you talking about this right here? So maybe there's an error. I'll have to take a look. Manually fit a vanilla partition model using R part of partition model on the train. Find the predictive value of the usage for someone who is not on the pay plan, i.e. this. Here's all their data right here. So we can only see one part of it apparently. Have a good night, Connor. We're doing just all that good stuff right there. Dealing right there. So we've got R part, usage, and we should say CP on that. I'm surprised we don't have the CP. We probably need to put in the CP. So here's the R part grid, and we usually need to give a CP equal to. So let's go ahead and grab our code right here. And let's go to the R part. So there's the R part grid. Let's grab this. We need to grab both of these. And let's see here. So let's go in here, drop in our code, take a look. And training. Okay. We got our part. Yeah. And I think we're using the right train data right now. Y tilde X, something's wrong with my code. My brain is not running full force right now. There we go. Our part. There we go. Clean up the code. Let's see. You're so intrigued. Awesome. I like seeing that. This, you know what this is, Carson, right now? This is decision trees. So stay here for a moment longer, definitely, because you're about to see decision trees. And is it doing that because of that? I'm trying to clean up my code to make it look nice and neat. I just want everything to look way better because I don't like it when the code looks crazy. It's going to do that. There we go. There we go. So this is much easier to read now and see what's going on. So all we're doing is predicting a y variable. We're doing the first part right now, so I think we're predicting usage. So we go right here, and I think it says, so find the predicted usage. Cool. So we go right here, we create our part grid, we create our tree. We go right here. Okay, oh, I know what people are doing, I think. I think I have an idea why there's a problem on this question. So we can look at the R part grid right here, and let's take a look. And then, Carson, you're about to see decision trees again. So you're about to be like, wait a minute, we do that in 201. The answer is yes, we do a lot of things throughout multiple classes that we do in things like 201. So let's go here and look at the R part grid on this and see what's going on. Okay, so what is our goal with this tree to minimize the what? I want to see in the chat. Who knows what our goal is? We want to create the smallest what. We want to create the smallest what right here. Like, how do we know this tree is doing well? And so you can see it in the graphic. How do we know this tree is doing well? Oh, the 5 on the second part. Oh no, we'll go do that one next. So I'll show Carson this right here, and then we'll go to the other one. So we want to create the one with the smallest root. Oh no, no worries. We'll go do that one next. We want to create the smallest root mean square error. So when we do this one right here, is this the one? Yep. So if you look right here, do I not have tree saved? Oh, I didn't do that earlier. Oh, well, yeah, I did it. Wait, let me look at this. 5 right here. There's the 5 part right there. Here's where we're creating our R part. We already created our tree model. And so let me go back to where I call my trees. What did I call it? I called it R part. So now we want to find out how it did on the R part. So we're going to go here and find the best R part. Did I not create R part? R part. There we go. And then we should be able to go to R part results. There's the results. There's all the results. So why is it not liking this? R part results, row names, best tune, R part. So unexpected symbol in tree. Oh, it's running that code right there. That's why. So let's go back to here, and I wrote the wrong thing there. So there we go right there. Here's the CP it wants to use. So this is the CP that we want to use that reduces it. Does everyone notice here that this says 27 right there, and there's no coincidence that that's where it's at? The one with the best CP is a CP that's very right there. See how it's 27, like 27.0001? So that's the best CP right there. And so what we're going to do is we're going to take this CP right here, and when we go down and make this R part right here, so we've got tree using R part, and so make sure we have everything right here. Let's go back, because I changed something. Oh. Hearing so many random noises outside. And then we should go here and say CP equals this right here. There we go. Now we visualize the tree, and here's the tree. Wow, that's a crazy tree. So this tree right here is a rather large tree, and you'd actually have to go through, and this is the fun of doing predictive modeling. So for anyone watching, I think this is the question we had earlier today, so I'm kind of glad to cover it, is how would you use this tree to make predictions? Well, one, we got to make it pretty darn large right here, which I can barely even read it. The problems of trees. And we got ambulance and stuff outside. And then we go here. Wow, I'm having a hard time reading that. A lot of times you can export to PDF. Let's export as image. Is that the best the image is going to look? rplot2. We got PNG, JPEG, all that good stuff. Let's go here, maintain aspect ratio, and go to 2000 and save it. And it was rplot2. Let's see if we can read it. Oh my gosh. So, pay plan, no, that is so hard to read. Low, there's the low value right there, and so we'd have to go back and look at the value of low. So sorry that's so hard to read. I swear there's ways to make it easier to read, but I don't know why R is not being happy today. So let's go here. We'd have to look at the value of low. And where are you at, low? And so here's the low is equal to 50. So then we have to look at this. It's so small. I know. I'm so sorry, Carson. Low is greater than or equal to 31. And the answer is yes. So we go this way. High, we can read it just barely. We can read it just barely on here. Let me try one thing. I'm going to try a trick right here, which I mentioned in class. I already have rattle on here. So that's why usually we don't do it by hand. We let the tree tell us. And okay, cool. This might be easier to read. It's just, that's probably not going to be easier. We'll remake the graphic now. Oh, we can finally read it. Oh my gosh, we can kind of read low right there is greater than or equal to. So if you notice, Carson, what we have right here is a decision tree, and we can finally almost kind of read it. We've got the yes and the no, low greater than or equal to 31, high less than 85, mean greater than or equal to 49, pay plan equals no, and you can see if you go left or right for the yes or no. So this is us doing decision trees and letting it make decision trees for us. It made a whole bunch of decision trees, but you saw this in 201, and now we're doing a categorical variable doing predictions, and then we can get down here to the bottom, and it can do the predictions for us. So hopefully, if the tree gets really big, it gets really hard to visualize. Now you can fix this. Now I wouldn't suggest it. This is not what we're going to do in this assignment. But if we put the CP, if we put the CP up to this, we should get a much smaller tree. Now that's much easier to read, and this only splits on low. But as you go to bigger and bigger trees right here, which CP is the complexity parameter, which controls how big the tree grows, then we have this right here. So you notice we're up to a bigger decision trees, and it's much easier to read now. Sorry, ours is just not like, it's like, you know, these graphics are too small, so when it does the pixels, it can't do it. But if you notice, this is just partition models, decision trees. So we still do decision trees in 474, and now we have a decision tree that's much smaller, much easier to read. And you could do this with the visualized model, the visualized tree. It'll look like that. So that's why. So you can use different CPs to make as many trees. Yep, and check this out, Carson. What you said right there is perfect. 474, chime in, because we're putting all the CPs through a what to figure out what tree to use. We're doing all the different CPs through a what. We put the CPs through something like this, because all of these right here, and then I think we have another one. Andrew has a question. I think Allie has 5 on the second part of the next one. We'll go do that, and then we'll do Allie's and Andrew's question. If you notice right here, these are all the values of CP that we tested. So we tested all of these values of CP right here, and we saw the different trees. You could go and you could make your CP grid smaller. So if you notice right here, I'm making my CP grid a lot smaller, and you'll notice there'll be a lot more dots in this graphic now, and I get a much more finer look at the right way to make the tree. You know how everyone keeps asking, Carson, like, how big should I grow my tree? Like, when is the correct size to grow the tree? That's the answer right there. That's the correct size. So what is the correct, like, how big do you grow your tree? Like, when do I stop splitting it? The answer is right there. The CP has suggested to us the complexity parameter is telling us that is, or the optimum complexity parameter for how big we should grow the tree is that, according to our analysis right here. When we start growing it worse, we do worse on the model. So we're using a RMSE. I love to hear that, because this is what they ask in 201. They're like, well, when do I stop splitting the tree? And here's the answer. Stop splitting it with that complexity parameter. Because in 201, I'll just be like, well, it's a very complex thing. There's a lot going on. You can make this even finer right here. So now you see there'll be even more dots. I mean, we're kind of zeroing in that's in this area. It's not going to change much, but now I just increased it by 5 times the amount of models. So I'm literally making all different versions of trees grown to all different sizes. And so when we look at the grid right now, it's going to have way more dots, but it's, you know, it's the answer is right in here. I don't think we're finding anything out massively different, but you can see just random other jitters in the model. But the optimum complexity parameter looks to be in this region right here, like wherever that dip is. And we actually went below 27 now, but yeah, that's how we figure it out right there. And so I think Ali was asking number 5 on the next part. So glad to have you here, Carson. I'm glad and the good thing is you can ask Andrew and them. We start you out in 320 with coding from the very basics. We don't throw you in and we're like, hey, code all these things. We're like, here's 2 plus 2. Like the very first code you write is literally doing this. Like, hey, there's 2 plus 2. And then we're like, hey, guess what? what do you think this will solve to? Like later we get to stuff like that. And that is the remainder of 5 when you divide it by 2, and that'll solve to 1. So we start doing that. What is the remainder of 10 when you divide it by 2? That's going to be 0. So you just have to know what each of these codes do. And you're basically just asking the computer. I love hearing that, Carson. That's so awesome. You're doing a great job, man. Like even just checking this out and seeing what we're doing will give you some groundwork and seeing how it connects. Awesome. 320. Yes. Carson, it'll be so good to have you. Like say, hey, you know how the classes work. I love it. Is this the one right here? The following chunk creates a decision tree using a different subset of the original data. Characterize the customers that have the highest probability buying. I'm looking for something like customers who spent more than, it's decision tree stuff. So we're doing the same thing. Customers who spent more than 900 and visited at least. So is there an error? If you're saying, Brian, there's an error. Oh, wait. Is this not it? So we want the customers who have the highest probability of buying. I'm going to use fancy trees and rattle because I like it. Okay. So what I really like about this is it color codes it. So let's zoom in on the picture a little bit. Is this the one we're talking about right here? We've got no behind me right here. We can see, I don't know, it only has one section. People are saying that. I wonder why their trees are only having, I just ran the code as is. It should have multiple sections. You might want to just, this looks to be the right answer, and let's take a look right here. Does anyone see the customers who have the highest probability of buying have done what? We need to go, remember, yes is to the left, and this is just like a 201 question, Carson, so really great stuff to clue in on here. And I love the way fancy plots look because it's easy to read them, and it's got the coloring. So what do we notice right here? The customers that have the highest probability of buying, would you notice what block they're in? Can anyone tell me what block they're in? The farthest left, the farthest right? Are they at the bottom? Where's the customers that have the highest probability of buying? The customers that had the highest probability of buying that we would predict would buy were in which group? Which group? Do you notice where they're at? And so you can basically, the far left, this group right here is the ones with the highest probability of buying. Because bottom left, you got, and does yours look like this, Andrew? Hopefully other people aren't having crazy issues. This right here encompasses 1% of the data. So these percentages down here in the fancy plot are what percent of observations are in here. It doesn't have the N for sample size. It just has percentages, and you might not be able to see it by my head and everything. I got to spin out of the way here. There we go. Oh. So you can see the percentages there. Right there. That's got a lot of the data, and then this one behind the mic has 47% of the data. So you can see a lot of the data is located in this area behind me. Only 14% of the data is located in these bottom terminal leaves. So these Carson right here are the terminal leaves of a decision tree. So we're looking at a specific tree right here and its specific leaves, and we're saying, what are the characteristics of the people most likely to buy? Well, they will have spent more than 8.8. We'd go to the left here. This is the yes side. They have visits that are greater than or equal to 6.5. They have a percent close that is less than 0.3. Got to watch the sign. Percent close less than 0.3. And their percent close is also greater than or equal to 0.062. So the percent close is somewhere contained between these values because I kept going to the left. Every time you say yes to one of these things, you have to go to the left. And I was trying to make it down to this area right here and just saying they're this, they're this, they're this, they're this. If you remember, we do this a lot with things like predicting if someone's in Greek life. You remember those examples, Carson? We predict like, is somebody in Greek life? Has somebody broken a bone? And what's pretty crazy, as I should be able to, watch this. What we should be able to do, where's question number 5 again? Hopefully, did that make more sense right there, Ali? And that should be the answer right there. We've got the set seed. We've got the purchase. So, yeah, we did the smoke weed stuff. So we were seeing if you had done that. You're welcome, Ali, so much. I think Andrew had a question. And I'll show you right here. I'm not going to do no, I should do predictive modeling. It's so easy to do predictive modeling. Because the first thing we're going to do is we're going to split our data into training and holdout. So watch this as I do a tool 1 example with 474 stuff. So all we're going to do is we're going to take our data right here, and we're going to go down here. Let's do a new data sheet. And we're going to put in here survey from 201 students. So we're going to go data, survey 10. And I don't know if I got it up. There we go. Okay, cool. I've got red class on. So now I have the survey 10 data from students, and survey 10 is just data from random students on questions we asked them, like percent funnier than, all these things. Let's bring back down our data so we can take a look at it. So if we were doing this as 201, we'd want to ask maybe a question about has somebody, where's my survey 10? Go right here. Let's try to predict somebody's GPA. So we're going to predict somebody's GPA right here. So we're going to make a model right now predicting someone's GPA. Well, first we need to do a holdout. So from this data set, because we're going to see how it works on new data, we're going to go here and we're going to take, let's say, 299 observations, and we're going to make it the holdout data. So we need to put survey 10 here, and we're just going to hold out this amount of data to test on to see how it works. Cool. So now we've created a training data set. The training data set is just, how many is it? The training data set has, we'll see right here, 299 observations. Well, let's do the other way. Let's do 400 observations here. Now the training set has 400 observations, and the holdout has the remaining observations, has 299. That's the way I want it. So now what we're going to do is we're going to create a tree-based model, and we're going to try to predict GPA. But we've already written all the code for this. The code is not going to change. We're going to go grab our tree from before and just use it because it already works. So here's our code right here, and there's only one thing I have to change. And Carson, I'm going to give you, if you even say any answer, Carson, you get 5 million points, but you get 10 million. If you can tell me the one thing in this code I need to change, if you can tell me the one thing, you get 10 million points. You can just take a stab at it. The one thing I have to change. You can ask any questions, but there's only one thing I have to change. I want to predict somebody's GPA, and I want to use this tree-based model to predict it, and there's only one thing I have to change right now. I'll let Andrew chime in, and Andrew can help out and help Carson get the 10 million points. So we only have to change one thing. Allie can help out too if she wants. There's only one thing I have to change to predict GPA. There's only one thing. Does anybody know? There's only one thing I got to change. Oh, no, it's all right. So there's only, think about this. So if we read this, this is the function. I know there's a lot to take in right now. I asked you a very hard question. But think about this. We're still using the train data. This is the type of model we're doing. This is how we're doing our fit control, which we already have the save. I'm not getting into fit control right now. But yeah, I know. Give you a hint. It has to deal that our last model was predicting something differently. Our last model was predicting a different variable. And so we have to change the variable we are predicting. Do you remember what the last model was predicting? Or can you look at the code and be like, looks like that model maybe wants to predict this variable. There should be something about the code in before line 10, like line 7 through 10 on what we were predicting. And then we want to predict something different. So great questions, Carson. You have earned the 10 million. So I appreciate you asking, like, can you give me a hint? And like, we're predicting something different. Do you remember what we were predicting last model and what we might have to change it? So we just have to change what we're predicting. So we'll no longer predict this. We were predicting buying, and we were predicting also usage. So we were predicting buying and we were predicting usage. And so this model, yes, let me double check. We are predicting usage, and the one before that we were predicting buying. You are correct. Buying was a model like 2 models ago. And this one was predicting usage. And what am I going to type right here, Carson? What am I going to type? You see usage in line 7. So what should I change that to? Since I want to, what should I write right there? Tell me the letters to write. Yep, you're getting it. I think Andrew's excited because he's like, you're getting it. So what should I change that to? Tell me what to type, and I'll type it, and then I'll run the code, and I'll see if it works. What should I change usage to? What should I type in for usage? It's what we want to predict. What do we want to predict? What should I type right there? I think you'll get it. I think you got it. Just think about what do we want to predict. So what variable did we say we want to predict? It's people's like scores in school. I'll get so excited. I'm like, yes! I'll give you a hint. It's 3 letters. It's the y variable we want to predict. So all that's going to go in here is the y variable, just whatever the name of the y variable is. You got it. Nice job. You earned that 10 million. And guess what? You've done it. You have now fixed the code with the original code we had. I think the graphic was too small. So let me try it again. Invalid graphic state. No. We'll look to see if our results finished anyways. I don't know why it's getting mad about the graphic. I just want to see the graphic. Wait, message warning. Oh no, we have an issue with the data. Okay. There were missing values in resample performance measures. So, of course, the data is going to be messy. But you did it correctly. Number of tattoos. Weekly hour of video games. You know what I might do? Let me try this. Let me try that. That looks to be working. Well, it's still getting mad. 1, 2, 3, 4, 5. Okay, let's try this. Really? Let's try something even better. Something weird's going on with the data. GPA is the name of the Y variable. There are missing values in resample performance measures. I'd have to look into that. GPA is 1, 2, 3, 4, 5. R part fit. Let's see what's going on right here. I will look into it. Info, train. Let me make sure we got the right train data. So, what'd you say, Andrew? I want to know, Andrew. R part, CP grid. Should be liking it. Let's try this. Let's try something else right here. Let's try GLM, and we'll just call it that for the moment. Tuning grid should have, oh, wait. Oh, wait, columns parameters. Oh, because we don't want to do a tuning grid right now. So, there we go. Okay, cool. Thank you for the suggestion, R. Okay, cool, that worked. So what we just did right here is we just created a linear model for it. So we literally just created a linear model, and we can go to, it's still called R part, but we can go to the results, and we can look at the R squared of the results for predicting someone's GPA. So if you look at right here, we can predict somebody's weight, which we'll probably have more success for, and then we can look at the results of predicting someone's weight. So all I did right here is change the method, and let me see, because we've got the CP. Okay, good, that should have done it. And this one takes alpha and lambda. So, oh no, email me that on Carson. I'll probably hop off here in a second because I'll start responding to emails. But I'm going to hop off. I broke the code. I'll have to look at why that R part wasn't working. But how are you doing, Andrew? I know it's going to be a late night. I'm going to go eat some more dinner, relax. But I'll probably hop off here. Are you doing all right, Andrew? I'm going to talk away from the microphone. Oh, no. Need to tighten up mic. I'll check it out, Carson. I'll take a look at it. I'm going to probably hop off and do work. I have a problem on number 3, but I can email. What is the problem? Which one is number 3? Is it this right here? Are you talking about this one right here, Andrew? Let's see, is it? I'll see. So it should be. Your GLMnet is saying that TuneGrid is an unused argument. It should be that. So if we go right here. Oh, yeah. You shouldn't. If you're doing just regular old vanilla, we're just doing vanilla 5-fold, I can't even think, logistic. You shouldn't have the TuneGrid because logistic without regularization, just vanilla logistic, won't have any tuning parameters. Does that make sense? So you should just remove the TuneGrid out of there because you won't have like an alpha lambda parameter, you won't have a CP or anything. So if you notice here in my code right here, there is no TuneGrid because you don't have any tuning parameters for logistic. Does that make sense, Andrew? There are no tuning parameters for logistic, just like I was doing. So great question, because that's what I was doing over here is I just ran, well, that's now a elastic net. Wait, no, the other number 3. Oh no, why are there so many number 3s? Other number 3, let's go to the other number 3. This one right here, okay. GLMnet, yes, you do need a tuning grid for this one. So it's saying this should do it right here. You might have to clean this up. I'll remove this in a second. Oh no, it's over the character limit. Okay. You might have to clean that up. I'll remove it here in a second. But since you've been here so long and working so hard, I'm just going to drop these in the chat to you right now. But check out what's going on with your code right there. Tell me when you have that all copy-pasted up. But that should be pretty much what you have. If you notice how my code looks, I mean, I'm basically showing it so anyone could figure out how to write what I'm writing right here. But since you're working on it, what I don't know what that means. Oh, what a G. I see what you're saying. I thought you were saying like wait a G, like wait a moment or something. The only difference in the mine is the order of the tune grid and the fin controller swapped. Oh, make sure you've got like capital G's here and stuff. Like literally, yeah, you're So make sure you have capital G's and all this stuff, because if one letter is not capitalized, so it's saying my GLM is saying tune grid is an unused argument. Make sure there's a capital. You actually wrote the question to predict on question 1.5. That's awesome. And so I think, yeah, maybe email it to me, Andrew, and I'll take a, I mean, yeah, Andrew, good. Email it to me and I'll take a look. Connor, did you have a bunch of people to help today? Did you give some help? Did you work with some people? How'd that go? And we really appreciate that. Like, I know a lot of students have been wanting help, and I think we've been doing a lot of help, so I'm really appreciative. I'm going to pass out. That is tomorrow. Tomorrow. Okay. Well, send me the code, Andrew. Carson, amazing job. Thank you for hanging out. Sorry I broke R. I usually break R, and then I have to be like, what went wrong? And you just have to be like, well, I got to troubleshoot this. So what are your hours? Remind me again tonight, and we'll send out reminders. Just say which ones you want to work. And because I think we're doing like Wednesday, Thursday, Friday, and I think we're going to do a good bit. Just send me the hours, and I'll send out a reminder, and then I'll ask the instructors to send it out. So probably do it like afternoon. Do it, yeah, start at noon if you can. Just if you can't, don't worry. But start at noon, and then when I finish up with doing what I'm doing, you might have a burst of students. And I'll try to do that so we can keep encouraging it. So that way I'll finish at noon, and I'll be like, hey, you know, Connor's going to be doing it. Remember, he's got the link right there. So awesome. Man, it's so I just feel so crazy that like I can look at the camera and you guys see me, so it's pretty fun. Okay, today ends the big streaming day. Tuesdays and Thursdays are our big streaming days. We're going to end with our Stat 201 intro right here. So I'll see everybody later. Thank you for swinging by. Bye, Connor. Bye, Carson. Bye, Andrew. So what are the chances the quiz? I'm going to do that. I'm just going to like send out a reminder, like make sure to be working them. Make sure to watch the review video. I'm going to do that, and I guess I'll do it the day after. Sorry for all the changes of dates. It's just whatever works, but good job, Carson. Good job working on them. So you get the inside info, Carson. Talk to you later, everyone. See ya. Bye.